everyone. Thanks for having me speak here. Sorry about my voice. I'm allergic to Iowa. I'll try to speak up as much as possible.
There's a microphone up there too. You clip on if you want to.
Is this okay? You can hear me? Okay. In case I made some bad
Otherwise,
words.
there's one you can hold too. You don't have to hand it to you. You see the larger one? The Monty Hall.
Wow, it's like Naruto.
You know? You just hold it, yeah. Hold it for about 5 seconds.
Hello.
Yeah.
Feels great. All right. Talking about a new class of prior, useful for Bayesian variable selection. Let's start with a linear regression model that y be the response, and x1 through x cubed your potential predictors. For example, y could represent the price of a house, and x's includes number of bedrooms, size of the lot, maybe some location information, and maybe some other less relevant factors as well. And let's say if you think this simple linear regression model would help you predict house pricing, then we end up with this expression with some error associated with the model. So nowadays it's relatively inexpensive to collect data, and you might have a lot of columns here not necessarily having in your mind they should relate to your prediction. They're just there in your spreadsheet. So our goal here is to identify the most relevant predictors, and at the same time we want a useful model that could do prediction and estimation, so we want the corresponding regression coefficients estimated as well. All right. There are many ways to do variable selection, more traditional ones like best subset selection, forward, backward selection. I'll skip right into a relatively more modern approach, penalized regression methods. So penalized regression methods will do variable selection and estimation of the coefficient at the same time by estimate beta with the minimizer of this function L of beta. So I'll give you an example of this penalty function P, for example, the famous Lasso penalty. To explain that a little bit, if you're going to find a beta that minimizes, so given a fixed lambda, let's say given a fixed lambda, if you want to minimize this function of beta, your beta should do a reasonably good job in providing a good prediction. So this term should be relatively small. But at the same time, there is a penalty on the size of the coefficient. Okay? And Lasso provides one way to penalize things, and this is kind of a linear penalty in the size of the coefficient. Imagine if you choose a large enough lambda 1. It turns out some of the betas will be penalized enough so that they completely reduce to 0. And by doing that, you're dropping the corresponding xj's out of your model. So you're doing variable selection. Of course, the choice of an appropriate lambda is a big deal, and typically this is done by something called tenfold cross-validation. I'm not going into the details here. All right, so Lasso is just one penalty function people like to use. There is some problem associated with it. Basically here, this solid black line represents lambda 1 beta on the positive side. And you can see as beta increase, it gives bigger and bigger penalty to that coefficient beta. But think about when the beta is really large, that actually represents this predictor is very useful in doing prediction. There's a lot of signal in here, and you don't really want to penalize it that much. Okay? When beta are large enough, you want to give it an easier time. So there are other penalty functions that produce less biased result than Lasso. If you let this penalty function flat out for relatively large betas. And one popular way to do that is to use the minimum convex penalty function. It looks like this red line. And exactly how do we flat this out? The simplest possible way is, if you look at the derivative, the rate of how the penalty increases is actually piecewise linear function. Okay, so just another alternative to lasso penalty. Now there are a lot more penalty functions, and in addition to lasso and MCP, I listed 3 others, and they all have this square term. So actually, lasso and MCP, they have their own problems as well. They have predictors that are highly correlated to each other. Then having this square term in the penalty will help make your prediction performance better, stabilize this. So just brush through that, and the most complicated line in this slide is what we call the MNet penalty function. So it's basically the MC penalty plus square term in the betas. But anyway, there are 3 parameters, hyperparameters involved. Penalty parameter, number 1, number 2, and some kappa, which is value in between 0 and 1. But anyway, 3 things you need to decide to use this penalty function. All right, so a summary of the relationship of all these 5 penalty functions. MNet actually provides the most general framework. If you set those 3 parameters, number 1, number 2, and kappa to certain values, you could end up with these special cases, lasso, EMET, ridge, MCP, and in other cases, there are general MNet penalties. And a headache is you have to use maybe cross-validation to choose a factor of 3 parameters. So let's look at the Bayesian version of these things. Recall we had Q predictors, x1 through xq. I'm now going to introduce an indicator vector gamma. Okay, it's going to be a binary vector. In a very simple case, if you have a total of 5 predictors, if my gamma is specified to be this, that means I'm going to select only 2 columns of this covariant matrix, and these are the corresponding coefficients. And a potential model that uses this subset of predictor is y equals to x gamma beta gamma plus some error term. Okay. Now how do I decide which gamma is the best one to use? Actually, I don't decide which one is. I will think about assigning probability to those gammas. Okay? So this line is actually just a different way to write down the last line on the previous page. I assume y even for this gamma, the subset of predictors follows a normal centered at x gamma beta gamma with some variability. Now, if you're doing Bayesian, you have unknown stuff you add prior to it. In this case, the coefficients, variance, and the model, the potential model are all unknown. So it could assign prior a joint distribution of these 3 guys. Okay? And the result is you end up getting a posterior distribution of all these unknown things. So for example, if you look at, by integrating out these 2 parts, one of the results you would get is, having observed the data, what's the chance that any one of these 2 to the q's power model would help predict, should be included in your study. And so that gives you a measurement of appropriateness of the model index by gamma. Just a few more details in that expression. Here, the distribution we assign to the coefficients beta. If gamma j is 0, that is, I decide not to include this j's predictor, you end up having the beta following this delta 0 distribution, which is basically a degenerate distribution at 0. So we dropped this j's predictor. On the other hand, if gamma j is equal to 1, that is, you do include this j's predictor, then we assign continuous prior to beta, say a normal distribution. In that case, this p would correspond to a squared function, a quadratic function of beta. Or more generally, as we mentioned, so many ways to choose this p. If you choose that as a penalty function, the analogy of a penalty function, you could choose this p to an net penalty. And in this case, you could also further assign prior to these lambda, which we call hyperparameters, if you want to do fully Bayesian analysis. All right. So now you have a Bayesian variable selection model. All inferences will be based on the posterior. It's a joint posterior on beta, sigma squared gamma. You could look at the marginals of some marginals of these distribution. For example, if you look at pi of gamma equal y, then you can find the gamma that corresponds to the maximum value for this posterior distribution. That's called the highest probability model. Okay. And another way to identify a model is to look at the marginal posterior probability. The chance you should include gamma j, that is in the data. It matters how important the j's predictor is. And if you collect all those predictor j that has posterior inclusion probability greater than a half, we call the result a median probability model. In terms of doing estimation and prediction, you could do Bayesian averaging over all models or a few top ones. For example, if you want to estimate for beta, you could just use the posterior mean of beta. And look, it could be written this way. And a nice interpretation is if you choose a certain subset of the predictors to do modeling, you could have an estimate posterior mean of your beta. And then if you do an average over all the 2 to the q's power gammas, you end up with this overall posterior mean. Some other things you can do are prediction intervals and so on. Okay. But one problem with doing Bayesian analysis is your analysis would involve the posterior distribution, which is known only up to a normalizing constant, and you have to do some high-dimensional integral with respect to it. So computing is a big issue. Markov-Chain Monte Carlo are computer-based simulation methods that can help draw samples from the posterior distribution and help you evaluate or approximate integrals. So we developed an algorithm belong to the MCMC family called the adaptive random walk Travis-Haskins within Git sampler. And that worked reasonably well for that problem. All right, so let's put our tool into use with breast cancer data. We got this data set that contains the gene expression measurement of that many genes from some 500 patients. And one of the genes, BRCA1, is the first gene identified that will increase the risk of early onset breast cancer. And our study here is to find genes related to that. Some initial screening allows us to focus on 655 genes that have sufficient expression levels and variations across subjects, and they are listed here. Okay, so I think there's the log of the expression level, and that's kind of our response to expression level of the target gene. Okay, so use the Bayesian MNet model I just proposed. Here is a picture of some of the inference you could do. Okay, so here on the x-axis are the 655 potential predictors. Okay, and for each of them, for example, let's say this one. For each of them, this center of this circle represents the posterior mean of beta j. And the size of this circle represents the posterior inclusion probability, the chi, gamma, j, given y. So the larger the circle, the more important this variable is. The more often you should include this predictor in your model, it's more useful. Whereas the size of the coefficients given here, and altogether, I also could provide a 90% credible interval, okay, to reflect the size of the coefficient and the uncertainty associated with that estimate. Some other things I could provide are prediction intervals. For example, I could write 90% prediction interval, we end up including 84% of the observations on the test set. That's about right. It's in the ballpark. Okay? So that's my summary page of my talk. We introduced a new class of prior, the Bayesian net prior. It allows more flexibility into Bayesian modeling. And we did some simulation studies and suggest the extra flexibility is useful in doing prediction and variable selection, especially when you have a grouping correlation structure in the predictors. On the other hand, what we contributed is a new algorithm for computing. Still, it's not completely satisfactory. In general, MCMC doesn't comfortably handle very high-dimensional variable selection problems. We have this gamma, which is to the Q's our discrete space. It's difficult for MCMC to do a good job. So there are alternative ways to do Bayesian computing that I'm currently exploring. And at the same time, maybe if the job is too hard, then lower your target a little bit. You could target inference that are less demanding on computing. For example, the median probability model I introduced earlier would be an easier target than trying to identify the highest probability model. So that's my talk. Thank you very much.